Hi everyone, and welcome to another lecture on computer forensics. I'm DSP, and today we're going to talk about file systems. So, what are files and why do we care about them in forensics? Well, why we care about them, it's pretty evident because files are useful abstraction for people to keep data in, and because most operating systems implement this abstraction for data management, um, we need to learn how to work with files in order to be able to uncover forensic data from them. So one thing we want to learn is how to preserve files, to extract them from a medium and preserve them for further analysis. We might want to undelete deleted files. Okay, this is very important because the suspect might have been able to delete files ahead of the investigation. So we want a way to actually get the parts of these deleted files and reconstruct them. We might want to look for data in places that normally shouldn't have data. So, for example, we'll talk about how we can hide data in the free space of file system, while most people wouldn't look for data in. And then we also might want to detect whenever a file has been tampered with, when the metadata doesn't seem to match with what we expect. And of course, there are more reasons. So a way that I like to think about files is as an object that satisfies an interface. And by satisfying an interface, I want to bring your attention here to this last set of calls. So I'm saying here that usually the operations you can do on a file, whatever that is, right, is, for example, you can read and write from and to the file. You might be able to seek to a different file position. You might want to open and close it, so that you have like a running file descriptor, a data structure that allows you to operate on that file and keep track of, for example, the positions that you have managed to seek in, or the position that you are currently after your last read on the file, or the same thing for the last write of your file. Then the operating system gives us a view of the disk as an almost infinite sequence of bytes that we can allocate and write our files in. Although, of course, we know the storage is not infinite. We have a certain amount of disk space, but the abstraction doesn't care about that. We potentially could create an infinitely large file. And then to identify a file, we know, for example, some things about it, like where it starts and its size. Therefore, we know where it ends, right? And ideally, we would like files to be isolated from each other. We don't want a user writing data into a file to start writing into space that is owned by another user's file. And this relates, as we say here, to the abstraction of memory that we talked about in the previous lecture. When you have memory pages that create the illusion that they're sequential, but the memory manager internally has them in a sparse layout and is chaining them in a way that they look as a continuous space to you. Now, on these operations that I mentioned here, different operating systems, and if you design an operating system in the future, you might make different decisions than what is established for now. Like, for example, in normal Unix operating systems, if you read some data from a file, the file position is advanced, and then if you read more data, you're reading from the place that you stopped reading before. Like, you can imagine the file position pointer is being advanced on every read operation. And if you decide to write on the typical Unix file systems, you're going to write at the file position that you were reading before. Like, so there is only one file position, and it's being shared between read and write. But if you design another operating system, you might decide to create two different file position pointers, one for reads and one for writes, if that makes sense in the workloads that you expect on files on your operating system. So on the storage media, on the other side of that equation is um, there can be multiple options. We might have hard disks, as we say here, HDDs, or hard disks on a RAID array. RAID means a redundant array of inexpensive disks. So it is a way to chain multiple disks together so that we can have things like mirroring or striping or other operations. These are efficient. For example, striping is useful to connect two disks and make them appear as if they're one bigger disk. And mirroring is useful for mirroring certain parts of one disk to the other, so we can have redundancy, right? So even if one disk fails, we can still have the data automatically written on another disk. And then you can have combinations of these modes. Or we might have SSDs, solid state drives, which are very ubiquitous now. We might also have things like networked file systems or Google Drive or S3 bucket somewhere that you're accessing it somehow, and it might look like a locally attached disk to your operating system, or a USB drive that you plug in, and that again looks like a locally attached disk, or a CD-ROM, if you guys remember what a CD-ROM is. But what we want to say here is that on all these vastly different mediums, you can still have the abstraction of a file operating on them. So you can create files on Google Drive the same exact way as you create files on a RAID array, or you create files on a CD-ROM. And that is the idea of interfacing here. You create this common interface, and the operating system takes care of making the correct connections in that abstraction, and the user doesn't really care what the backend looks like. So let's talk a bit about how to collect data between these interfaces and how they differ. Again, I mentioned on the previous slide that we might have different modes of disks. Again, here I'm mentioning certain acronyms that you might find around and what they actually mean. And again, I might be wrong on having looked up these terms. For example, I'm not really sure that ATA stands for Advanced Technology Attachment, but quite sure, but not absolutely sure. So you can let me know. So we have, as we said, all these backend differences, but also in the on the front end of on the other side, we have like Unix types of files. We might have Windows types of files, right? We might have Android files. Are Android files different than Unix files? Maybe, maybe not, right? Or the Apple file system, you know, on a Mac, is that different? They still look like files. Like what is the set of common things you can do on them? Well, I'm just hinting at you here that all the things that I described, like open, close, read, seek, and all that stuff, are kind of common between all these types of files. Okay, but some of them might not be. That doesn't mean that you know, there is an agreement between all these different operating systems that, oh, that's exactly how we define a file. Okay, so looking at the disks now, and why this is important is because we still use some terminology from the age when everything was still a disk. You know, HDD stands for hard disk drive, and here in this picture you can see certain different parts. Okay, we have, for example, the platter. The platter is this magnetic surface around here that looks like a vinyl, right? Only it's very similar to vinyl, only it responds to magnetic inputs, and you can actually measure its magnetic properties and get an output out of it. Then we have spindles in here. We have the head that is on top of the actuator arm here, and the actuator arm can move, as you see, like it can have a range of motion like this. Again, like similar to a vinyl player. And the actuator axis over here. And as we say, there are multiple platters that can be stacked, one on top, and there might be others below. And these platters are rotating. Okay, they can rotate very fast. They can even do like 15k rotations per minute here. And as these platters rotate, the head that is sitting on top of the actuator arm, and the actuator arm can also move left and right, it can cause an electromagnetic pulse, and by that it can write, or it can just read from the electromagnetic disturbance in the field. It can read and infer what value of a bit is written on that certain part of the disk. And as I said, by changing some properties here, like voltage properties, it can read on other platters that can be sitting below this platter. Now, again, as I said, this moves from here to here, and therefore it can read potentially everything that passes underneath it. Okay. But this again needs to move, right? If it doesn't move, then it will always read whatever is under this circle. It needs to move over here, for example, to read whatever is under this circle. And physically moving the actuator, you can imagine that takes, because it's a mechanical movement, it will take a lot of time compared to just making a measurement, a digital measurement, okay? Because we need to have a physical move. So again, that's why I'm hinting on why this is slow, because we need to have a mechanical process, and I'm saying here this requires at least an order of magnitude of latency compared to just reading something from a chip, but it might be at least a couple of orders of magnitude. So this might be an understatement that I'm writing here. And what is the problem that we also have? Like, you can imagine that if we put something in motion, like if we start putting the arm in motion to go from the inside of the disk to the outside, for example, because of Newton's law, if something is in motion, it will tend to remain in motion unless we put an unbalanced force on it, right? Therefore, in order to make the arm stop now from where we made, start going, in order to make it stop, we need to expand energy, right? We need to physically stop the motor of the arm so that it doesn't go further and it stays in the middle that we want it to, for example, to read some part of the disk. Therefore, because we're expanding energy for that, you can imagine that this is a slow process. Therefore, we need good algorithms, or we need to start coming up with ideas so that we don't move that arm very often, right? We want to be efficient in how we move that arm. So, for example, if we are going to start moving towards the center, we might as well commit all the way that it will actually make it to the center and then start going back, because it's possible that if we start going like from the outer part of the disk to the kind of the center, and then turns back to the outer part of the disk, then back to the center, then back to the outer, that might be quite inefficient. And what I'm mentioning here is that we have come up with the idea of placing indexes at certain part of the disk that help us make an informed guess on where to not guess, actually, an informed decision, I should say, because we know where what we want to read is at, to jump to. You can click on this video here, and you can see disk in action while it's doing certain reads and writes, and you're going to get a better feeling of what I'm trying to convey now after you have seen it. And you will see on this specific example that it's going to stay a bit on the outside. Probably it's trying to find some files and goes towards the inside, starts trying to find the actual blocks that comprise the file, then go back to the outside, find another file, then go back inside and try to read the next file, and so on. So to have an idea of some terminology here is, for example, we have the geometric sector, okay, here, that is colored in this bluish hue. And the geometric sector is just an area between two different angles, right? From angle phi1 to phi1 to phi2, there's like this geometric sector. And then a track is just a concentric area on the disk, like this. So a sector is just a part of a track, okay, between two angles. Okay, that's what we define as a sector in the disk. And a block or a cluster is a certain number of sectors in that disk. So in order to start making this subdivision, this is just like an agreement that we can have on splitting a disk into a certain number of sectors, right? And you can see here that if we choose a size of sector that is like that big, then on this on this radius, then that tells us how many sectors in total this disk can have, right? But if we choose, for example, a sector that is, for example, that big, right? Like take up a quarter of this this angle, like 90 degrees here, then if this is our sector size now, then we will have a different total number of sectors on the whole disk. I hope you can see graphically that. Okay. So this is again something that we decide when we create a disk. Okay. Now like for hard disks, usually a typical size that you see this sector having is 512 bytes. Okay, I mean that's almost half a kilobyte for a sector. Okay, for CD-ROMs, because they have other density on the medium, this can be like 4 kilobytes. Okay, and again you can kind of imagine here that because CD-ROMs have a laser that is reading, an optical surface compared to some magnetic property on a read-write medium like a magnetic tape, like a disk, you can see intuitively why a CD-ROM would normally have higher density on a sector than a hard disk. Okay. Now, a block now is a bunch of sectors. Okay. And this is something that we control at the file system level. We say that we want a block to be a certain number of sectors. So for example, if we want blocks to be of equal size between CD-ROMs and hard disks, okay, we would have a block on a hard disk being more sectors than a block on CD-ROMs, right? Because of different density that we have here. Okay. So now, having talked a bit about what is a file system and having talked a bit about how the devices that hold the data look like, then we would like to find a data structure to represent a file with. Okay, so we could say, for example, that we want a file to be a certain number of blocks. Okay, like let's say, for example, we make a very simple operating system. We say, okay, we want to give the We want to give the capability to the user to have files, but we don't want to write too much code. So we're going to say that every file is going to be, for example, 4 blocks. Okay, so going back here, we can start and we say, okay, again, a block is like, for example, here, like 3 sectors. So we're going to take 3 sectors here, and you know, we said we want like 4 blocks, so it's going to be 12 sectors. Okay, so this is one file in our file system. So if someone wants to write more data, sorry, we cannot support that. If someone writes less data, then we'll still use 4 blocks for that. Okay, that's simple, but it's probably not very efficient. What if we use, for example, a linked list of blocks? So we take some part at the end of the block to point to the next block. That could work, okay, but you can imagine probably from your computer science background, like that if we start going through the linked list of blocks, then probably we can just scan in the middle of that, seek to the middle of that. We have to start from the beginning and progressively walk the list of blocks until we find what we want. So we can really have seek in that case, right? But what if we have like something like a telephone book, right? When we have like certain entries, we have one entry for every file, and that entry is called an inode. Okay, if we have an entry for every file, and on the entry we have a list of the available blocks for it, then we could potentially seek, if we have that list in an ordered fashion, we can say, if I want to go in the middle of the file, okay, I'm going to the middle block of that list, right? That's approximately the middle of the file. And then I can also have other metadata in that inode, right? I can keep track of other things there, like, for example, the file owner or the permissions of the file and all that stuff. So that seems like a useful idea here, keeping certain parts of the disk for the inodes and other parts of the disk for the actual data blocks. So that's the idea that we'll look more into the next set of slides here. What I want to say here is that you will see that on the inodes we decide we don't keep the file name. There are reasons for that, because the file name has a better place to live in, and we keep the file name into what's called the directory entry. So we have special files that are called directories, and the special files have the file names of other files in, right? And this allows us to create a hierarchical tree-like structure that contains names to files, and then the actual file contains the pointers to the data blocks. Okay, this for this video, and in the next video we'll talk more about how inodes look like.